Definite matrices. 7.1 refers to the solving polynomial systems notes. So let's fix a real vector space of dimension n. So V is an n-dimensional real vector space, and with or without basis, right? So if we have a basis, then quadratic forms on this vector space are represented by n matrices. If you have a basis, namely by symmetric n matrices. So if you have a quadratic form phi from V to R, and U is a vector in the vector space, then we have the usual representation by a matrix X. So capital X is a symmetric matrix, n matrix, that represents the quadratic form phi with respect to a fixed choice of basis. And U here is a column vector in R to the n. Now, from undergraduate linear algebra, you know the spectral theorem, which says that you can diagonalize quadratic forms. You can diagonalize over the real numbers. Symmetric matrices can be diagonalized, and the tropically inclined among you, of course, already thinking about ordered fields with evaluation. So all you need is that this is a real closed field. So if R is a real closed field, then you can diagonalize symmetric matrices. So and I'm going to write lambda for the matrix that diagonalizes X. So lambda transpose times X times lambda is a diagonal matrix. On the diagonal we have lambda 1, lambda 2 up to lambda n, and those are the eigenvalues, and these are real numbers. They are in our real closed field. And then the matrix U is an orthogonal matrix, and the columns are the eigenvectors. Okay. So this is the spectral theorem. The eigenvectors are real and they form an orthogonal basis, and the eigenvalues are real. Now note that with this diagonalization comes a sum of squares representation of phi. Right? So you can write phi now as the sum j from 1 up to n, lambda j, those are the eigenvalues, and then the sum I from 1 up to n, lambda ij, that's the entry in row I and column j of the lambda matrix, times ui squared. Okay? Well, really this is combining these, regrouping sort of on the board, right? So if you take this formula and you replace hope maybe I have the inverse here. Okay, so in the new basis, right? So if we replace x by this, and we're multiplying with u transpose on the left and u on the right, right? Then this is a scalar, right? Then the scalar u transpose lambda transpose x lambda u, that's a number, right? And that number can be rewritten like this. Okay, just sort of regroup by distributivity and so on. Okay, so here's the first result, proposition 7.1. The following are equivalent, the following 5 conditions are equivalent for a symmetric matrix. X is a symmetric n by n matrix having these eigenvectors and representing a quadratic form. then the following conditions are equivalent. That's the positive semi-definite condition. So first condition is the quadratic form U transpose X U is greater or equal to 0 for all U in R to the n. Okay, so the quadratic form, just as a function, attains only non-negative values. That's condition A. Condition B says all eigenvalues of the matrix X are non-negative. We know they're real numbers, but here we're saying in condition B they're all non-negative real numbers. C, all principal minors of X are non-negative. So there are 2 to the n principal minor. So by principal minor, I mean a subdeterminant. So the determinant of a submatrix that uses the same row indices and the same column indices. Okay, so there are 2 to the n subsets of 1 up to n. So pick any such subset. Use that to pick the rows of a submatrix. Use the same columns. That gives you a principal minor. And then the determinant should be a non-negative real number. Okay? So there's one 0 by 0 minor, which I declare tautologically to have determinant 1. There are n 1 by 1 minors. Those are just the diagonal entries. They should be positive. The n choose 2, 2 by 2 minors, and so on. Okay? D is there exists a matrix B in an n by n matrix over the real numbers such that X can be factored as B times B transpose. Okay, so that says the matrix X has a square root in this sense. Okay, so we can take the square root, we can factor X as B times B transpose over the real numbers. And finally, the quadratic form is a sum of squares. Form phi is a sum of squares. And today and tomorrow I'm often writing SOS for sum of squares, but over the field of real numbers. Okay? So let's look at these. I mean, some of these equivalences are easy, pretty immediate, from what we've done here. So for example, well, if phi is a sum of squares, then obviously it's non-negative. But for quadratic forms, the converse also holds, right? So for example, well, you look at this representation. I mean, this function as a function of u, is non-negative if and only if these multipliers lambda are non-negative, and they are the eigenvalues. So you can see that. Here you get the factorization. So for example, one of these factorizations you can get here. So this kind of factorization I will call a Cholesky factorization. Okay? So I'm going to be a little bit loose on the definition of Cholesky factorization. So back as an undergraduate, when you took your numerical math class, linear algebra class, your professor probably gave you a more rigid definition of Cholesky factorization. So B has to be upper triangular or something like that. Or if you go on the wiki, there's some requirements. For me, a Cholesky factorization is any factorization like this. So on the homework, on the exercise sheet number 1, anything like this I'm going to allow as a Cholesky factorization. But of course also, if you were given the eigenvectors, you can write down one such Cholesky factorization. So B is lambda times the diagonal matrix with entries square root lambda 1, square root lambda 2 up to square root lambda n. So that's an example. That's a Cholesky factorization of a positive semi-definite matrix. Yeah? So if the eigenvalues are non-negative, we can take their square roots over the field of real numbers. And then this is an example of a Cholesky factorization. And C requires a little bit of an argument, but I think many of you have seen these equivalence classes. So the set of these matrices, so these matrices are called positive semidefinite. Okay, so a matrix is positive semidefinite if it satisfies one and hence all of these 5 equivalent conditions. So let's use the notation PSD of V. So this is the set of all quadratic forms. So sim to V, right? So this is quadratic forms on V, right? The second symmetric power, or possibly the dual. Luke helped me out, right? So we'll talk a lot about this kind of stuff here. So this is the set of symmetric n by n matrices such that phi satisfies these conditions A through E. Okay?
So because you need 2 elements of V.
Exactly. Okay. So this set is a closed. So this has various properties, right? So a matrix either satisfies this or it doesn't. Okay. So now we're talking about the set of n by n matrices that satisfies this, and this set has a number of structures, all of which are very important. Namely, it's closed. It's a closed subset of the space of symmetric matrices. The space of symmetric matrices, this sim 2V, is a real vector space of dimension n plus 1 choose 2, and this is a closed condition. It's full dimensional. It has the full dimension n plus 1 choose 2. It's basic semi-algebraic. It is convex, and it's a cone. Okay? Each of these words is important. Okay, so let's read this together. Right? So it's a closed, full dimensional, basic semi-algebraic, convex cone. Okay? So what do these things mean? Well, a convex cone in a finite dimensional real vector space is the intersection of a number of half spaces that go through the origin. Okay? So it's the solution set to a system of homogeneous linear inequalities, a linear form greater equals 0. Right? That's what it means to be a closed convex cone. So closed convex cone means your solution set to a system of linear inequalities, a homogeneous linear form greater equals 0. And another one, and another one, and many of them. Well, that's A. Right? From the point of view of X, so we're trying to characterize X. So if Matt gives me a U, he gives me his favorite U, then Matt's U gives a linear inequality on X. This inequality is quadratic on U, but if he fixes the U, it's linear in X. Okay? So A is an infinite, uncountable system of linear inequalities, and that shows it's a closed convex cone. Right? So A shows it's a closed convex cone. Now why is it full dimensional? Well, the identity matrix, pick the identity matrix. That has this property. It has eigenvalues 1, 1, 1, 1, 1. The eigenvalues are continuous functions, right? I mean, of the matrix entries. So if you wiggle a little bit, the eigenvalues will still be positive, right? So if you pick an open ball in the n plus 1 choose 2-dimensional space of symmetric matrices, an open ball around the identity matrix will be in this set. Okay? Okay, so it's a closed, full-dimensional convex cone. Now, basic semi-algebraic. Let me explain that. Okay? So a semi-algebraic set is one that can be described by a Boolean combination of polynomial equations and inequalities. That's a semi-algebraic set. And Boolean combinations are, and, or, not, the usual stuff, right? That's a semi-algebraic set. A basic semi-algebraic set is a semi-algebraic set that's given as the conjunction of a finite set of polynomial inequalities. Okay? So basic semi-algebraic means you have a bunch of polynomials. So if it's closed, right, it should be given by f greater equals 0 and g greater equals 0 and blah 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 and maybe, you know, h greater equals 0. A finite list, a conjunction of finitely many polynomials greater equals 0. Okay? So why is that different from semi-algebraic? Okay, so let me illustrate that. So for example, let's look at the plane and let's look at the equation x equals 0 and y equals 0. Okay? Well, there are 4 orthants, right? So for example, x greater equals 0 and y greater equals 0, you know, that is a basic semi-algebraic set. Okay? Let's take the complement. Okay? So let's look at not this. Okay? Then, you know, and then you get, you know, the open part over here, and let's make it closed. Okay? So this is x less or equal to 0 or y less or equal to 0. Okay? I claim that this is not basic. Is not a basic semi-algebraic set. Okay? So you take 3 of the orthants in the plane. That is not a basic semi-algebraic set. Okay? Let's think this through. Okay? Suppose this were a basic semi-algebraic set. Well, suppose you could write this as the solution set to f greater equals 0, g greater equals 0, and so on and so on. Then among these f's and g's, x and y have to appear. You think this through, right? But then, you know, this is disallowed, right? This, you know, x sort of sticks through the interior, right? That's basically the obstruction, right? So this is the obstruction to being basic semi-algebraic, okay? So over lunch, when you talk to the experts, so these 2 wonderful people, Xiaostein and Reiner, they're the experts on real algebraic geometry. So you guys can discuss this over lunch. This is a semi-algebraic set that's not a basic. But the PSD cone is fine, right? It's a closed, convex, full-dimensional, basic semi-algebraic set. Okay, now in this space, Sim2, we have linear forms. So linear, well, let me actually start again. Give ourselves a little space. Now I want to talk about linear forms in our space. So linear forms on the space of symmetric n by n matrices have the following representation. Well, what do I mean by this? So this is the dot product. So X is a matrix of n unknowns and A is a fixed matrix, and this is just the dot product between 2 matrices, right? You multiply each entry with each entry. But the way the engineers write this usually is as trace AX. Okay? So this is, you know, so for fixed A, again, mat gives me a fixed matrix A. Then this is a linear form on X, on the space of symmetric matrices, and this is the dot product, right? So if you work this out, right? So trace of a matrix is the sum of the diagonal entries. So this is A11 times X11 plus A12 times X12 plus A13 times X13, okay? But this is sometimes convenient to write it in this trace form. These are linear forms. When I talk about linear functions, I'm sometimes a bit imprecise. So let me just say by a linear function, I mean a inhomogeneous linear function. So it's a linear form, you know, ai x plus or minus a constant. Let's say minus bi. So when I say a linear function, I mean a linear form minus a constant. So li is represented by the matrix AI, and the right-hand side, BI. Okay.
So what do you mean by Li? Why do you have index I in the subscript?
Well, we're going to have a couple of them, because now in about 3 seconds I'm going to define semi-definite programming. Okay? So now we're ready for the definition. So semi-definite programming is the following problem. So there are two versions. There's a decision version, and then there's an optimization version. Right? There's always an optimization. You have this sort of decision versus optimization. So decision says, can you do something? Can you find a traveling salesman path that visits, the 10 largest city in Korea that takes less than this many kilometers? And the answer is yes or no. And your computer science friends, can put this in the class NP or P. So that's a decision problem. Okay? The optimization problem says, what is the shortest route of a traveling salesman tour through the 10 largest cities, in Korea? And that is a number. The output here is a number. And so from a complexity point of view, this would be in something like sharp P or sharp P complete or something like that. Okay? So the decision problem is to solve a linear system of equations. L1 equals blah, blah, blah. Lm equals 0. And I forgot to say the most important thing, because I just got reminded that that answers your question. So on June 25th, digression. So on the 25th, I'm going to have an exercise session in the afternoon. On the 26th, I'm going to have 2 guest lectures. And the 2 guest lectures are, Sang-Il is a combinatorialist, the combinatorialist here at this department. And then the other one will be David Tyun, who's an algebraic geometer from PostStack, the other school. And the idea was that you guys should meet sort of the local mathematicians and find out a little bit what they do. So David, for example, is the unique person who occurs with multiplicity 2 at the list of program organizers of next year's SciAm algebraic geometry meeting. So if you go to the website, SciAm 2015 Dijon algebraic geometry, there's an organizing committee, and there's a local committee, I am on, and then David is the unique person who is on both committees. So aren't you interested why that is and who he is? So he will speak together with Sang-Il 2 fabulous lectures on Friday afternoon, 26th of June. Okay, so decision problem is solve a linear system of m equations, L1 equals 0, blah, blah, Lm equals 0, subject to the condition that X is in our cone, is a positive semi-definite matrix. Okay, that's a decision problem. Can we find a positive semi-definite matrix that satisfies a linear system of m equations? The optimization problem says let's maximize a linear function. And let me call that L0. So there's one more linear function. I want to maximize or maybe minimize that subject to the previous conditions. Okay, so subject to these things. Okay, so the decision problem, we're just saying, does there exist a positive semi-definite matrix? And in the optimization problem, I want to find the best one. Best in the sense that it maximizes a linear function. Okay? Now, maybe let me take a poll. Who here is familiar or has heard of semi-definite programming? So 1, 2, 3. Okay, so about a third. Okay. Now, probably more of you are familiar with linear programming. So linear programming. Just out of curiosity, is there a course in the KAIST math department that teaches linear programming? No. Engineering? Engineering probably has a course. Maybe engineering, not the math. How about post-tech? Course in linear programming? Okay, I'm just curious. Okay, so linear programming is a special case of semi-definite programming. So it's the special case we get by restricting to diagonal matrices. Okay, so suppose all the matrices that are involved, m of the matrices that are involved here, or m plus 1 of the matrices that are involved here, suppose they're all diagonal matrices. Suppose A1, for example, is a diagonal matrix. Well, if A1 is a diagonal matrix, well, then, you know, this x will exist. It will only depend on the diagonal entries. Right? So you're not ever going to look at the off-diagonal entries. Right? This is just picking out linear forms of the diagonal entries. So you might as well restrict to the diagonal entries. And then the condition is simply whether the entries are non-negative. Right? So then this PSD cone gets replaced just by the non-negative orthid. Okay? So the special case of semi-definite programming that you get by taking diagonal matrices is called linear programming. Now, the yellow set of feasible solutions, we'll talk more about this, is called a spectrahedron. So this set, the set of all x in the PSD cone that lie in this affine space, is called a spectrahedron. And if you restrict to diagonal matrices, this is called a convex polyhedron. So a spectrahedron consisting of diagonal matrices is called a polyhedron, a convex polyhedron. A convex polyhedron that's bounded is called a convex polytope. Spectrahedra may be bounded or unbounded, although in the pictures that we'll draw, they're usually unbounded. They're usually bounded.
So when you say restricting, you mean the x is restricted to diagonal matrices or the AI?
Yeah, the AI are restricted, but then you can also, so if the AI are restricted, then these linear forms only pick off diagonal entries. And then here, you could either take x to be a symmetric n-by-n matrix, or you could just restrict, you know, look at the diagonal entries, and the problem will be the same. Yeah. Okay, so this is it. This is semi-definite programming as defined in Chapter 7 of the notes. Okay. Now that is actually not a good source for this material. There are much better sources. So a very good source to study about semi-definite programming and the connection to algebraic geometry is the book by Bleckermann, Parillo, and Reka Thomas. So that book, it's on their homepage. You can download it for free. That appeared last year in the SciAm series, and I think the title is something like Semi-Definite Optimization and Convex Algebraic Geometry. And that gives a wonderful introduction to these themes. And on page 11, you find duality theory. So I'm going to state for you now semi-definite programming duality as stated in the notation of page 11 of the book by Bleckermann, Parillo, and Thomas. Pablo Parillo is the first speaker on Monday. So coming Monday, I think at 9 or 9:30, I forgot, he will be the first speaker. So he is an engineering professor at MIT and really sort of a leading figure, you know, in this field. Greg Bleckermann is one of two main program organizers for next year's SciAm Algebraic Geometry Conference. So one is Joachim Rosenthal, who does cryptography, a popular topic in Korea, and the other one is Greg Bleckermann. Reka Thomas, I believe, will be an invited speaker next year. and she gives phenomenal talks. So these are the authors of this book, and the other people contributed chapters. So the primal formulation is like this. So it's basically, this formulation. I'm just going to change notation a little bit. So in their formulation, you don't maximize a linear function, but you minimize a linear function. And the cost function is called Cx rather than L0. Okay, so you maximize a linear function given by a cost matrix C, subject to x funny greater equal 0. So this means positive definite. Okay, so this saying x funny greater equal 0 just means that x is in the PSD cone, and then you have a linear system of equations. AI x equals bi, and I think now I'm consistent with the notation over there for I from 1 up to m. Okay, so that's the primal formulation. Minimize a linear function Cx subject to m linear equations and non-negativity constraints, in the sense that we want the matrix to be positive semi-definite. Then the dual is the following. The dual is maximize. Now, at this point, I like to appeal to linear programming, and unfortunately not taught at Postec, So the way this works in linear programming is you have a cost vector, C, and a right-hand side vector, B. And when you pass to the dual, they trade their role. Right? So the guy who was the right-hand side vector on the primal becomes the cost vector on the dual, and vice versa. Okay, and it's the same here. So the way this works is maximize B transpose Y subject to A1 Y1 plus 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 AM YM funny less or equal to C. Okay, let's unravel this. Okay, so in this dual, the decision variables are y1, y2 up to ym, and they form a column vector. Those are the unknowns, the decision variables. We want to find a column vector y with m coordinates. Okay. Now I want to maximize a linear. This is just a dot product of two vectors. So B transpose is a row vector with these coordinates bi. We just take the dot product, b1 times y1 plus b2 times y2, and so on. Okay. Now this is a linear combination of matrices. So y1 is a scalar times this matrix, blah, 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 blah. So this is an m by m symmetric matrix whose entries are linear forms in y1 up to ym. And less or equal, that means that the difference matrix, this symmetric matrix, minus that symmetric matrix is positive semi-definite. Okay, so inequality is sort of in the conic sense, right? So C minus the left-hand side. So these are dual. Okay, so what does dual mean? Well, dual means various things. In particular, it means the following. So lemma 212. So this is one source. Now, there are many, many, many other sources on semi-definite programming. Okay, so for example, next week we have two of the principal speakers will be, Koreans and ladies, and they're sort of expert. One of them, is experts in optimization, and they will probably refer you to Boyd's book. So there's a book by Boyd and Vandenberg on semi-definite programming, again for free online. These things are available as PDF, legal online for free, and it comes with software. So the software that Steve Boyd and his group developed is called CVX for convex, And there are many other software packages. Again, you know, Feng and Rainer can tell you how you do this in practice. So if you're dying this afternoon, you should be dying to use MATLAB or CVX or something to do the exercises, then you're ready to go. Okay, so lemma 212 in Bleckerman, Parillo, Thomas's book says the following. Let x and y be feasible solutions. That is to say, x is a feasible matrix for the primal problem. Okay? So x is in the spectrahedron for the primal problem. It's primal feasible, meaning it satisfies, you know, the equations and the equations and the inequality. And y is a vector that again satisfies this inequality. So it's feasible in the dual. And they also satisfy something called complementary slackness. Complementary slackness. And that's the following condition in this context. So we look at the two matrices that are supposed to be positive semi-definite. So there's the matrix from the dual, that's the difference, right? So this one minus the left-hand side, that's a matrix. And that's the matrix we want to be positive semi-definite. And on the primal, it's just x. We want to be positive semi-definite. And complementary slackness says that this is the zero matrix. Okay? So we have the product, the matrix product of two symmetric n by n matrices. And we want the product matrix to be the zero matrix. So this satisfies, so this is a system of many bilinear equations, linear in x and linear in y, quadratic altogether. Okay? So if that is all the case, that's the hypothesis, then x is primal dual, is primal optimal, and y is dual optimal. So if some wizard can give you a feasible solution of the primal and a feasible solution in the dual, nothing about optimality, right? And if these quadratic equations happen to hold, then you can be sure that both of them are optimal solutions for their respective problem. Period. Okay? Yes?
But usually in LP, when you go to dual, it's still LP.
Yes.
Is this
okay. Yes. So these are both semi-definite programs. It looks non-symmetric. So the appearance is that the primal looks different from the dual. But it's not. So you can rewrite this in a way, you know. So I always criticize these people because I don't like this formulation. But that's the formulation everybody uses. Okay? So in the first 3 or 4 chapters of this book that was written by these people, you know, you find the standard formulation that you always find, and they look a little different. But they're both SDPs. Okay? In chapter 5, that I was an author on, there's a symmetric formulation. So there's a way of rewriting this, but it takes a couple transformations. But you can rewrite it in a way that this one looks exactly like that one. Okay? They're both SDPs. What else? Yeah, okay, so this is weak duality. So let me state strong duality. At least give you a hint. So, okay, so in 215, the converse holds sometimes. If both programs are strictly feasible. And in optimization, this is called Slater's condition. So what does that mean? Well, here I'm just saying, the hypothesis. So here we have an if-then statement. So if, x and y are feasible, let's suppose that, then this implies that, right? I would like to say it's if and only if. I would like to say, complementary slackness holds if and only if the two solutions are optimal. It's not quite true. It's almost true. Namely, if x is in the relative interior of its spectrahedron. Okay? So if you can I'm sorry, if both problems, okay. If this spectrahedron has a solution, x prime, where we have strict inequality here, we're in the interior of the positive definite column. Okay, so we're given the x and the y. So Abraham gives me an x and a y. Okay, so now I ask this program, dear program, are you strictly feasible? Right? Does there exist some other x prime that has all its eigenvalues positive, strictly positive, and also satisfies these equations? Okay, okay. Then here, does there exist some y prime, y1 prime, to some other linear combination such that the difference matrix is positive definite, all eigenvalues strictly positive, all principal minus strictly positive? Okay, if that is the case, then we can go the other way. Then every pair of primal optimal and dual optimal solution comes by solving this equation. Okay, so in practice, for this class and for this afternoon, you can assume it's if and only if. Okay? It's a little bit like the second derivative test in calculus, right? So you always assume, your students first think it's an if and only if until they, get only partial credit on the first exam, and then they realize, it wasn't an if. So assume it's if and only if until you get partial credit. Okay? So that's duality. So software, I already spoke about this. There are lots and lots of software packages that you can try. And let's do an example, a numerical example. Here is a problem. Minimize 4x12 plus 6 x13 plus 10 x23. So this is an example where m and n are 3. So 3 linear equations, and I'm working on 3 by 3 symmetric matrices. Overall matrices, I'm going to call them concentration matrices. So what's a concentration matrix? It's a positive semidefinite matrix, and here I'm going to take this to be 3 by 3 such that the diagonal matrices are 1. Okay, those are concentration matrices. Okay, so this is an example of a semidefinite program. So maximize this linear form: 4x12 plus 6x13 plus 10x23, subject over all positive semidefinite 3 by 3 matrices that have 1s on the diagonal. Okay. Now, why are they called concentration matrices? Well, that brings us to statistics. I'm really sorry, in July I'm going to talk a lot about statistics. So one thing that statisticians do, they look at covariance matrices. The covariance matrix is an element of the PSD cone. Okay, so in statistics, a positive definite matrix is a covariance matrix. It's a matrix that represents a Gaussian distribution. Okay? Now, what statisticians sometimes do, they normalize the variances to be 1. So that they can focus on the covariance structure, and then you get a concentration matrix. So concentration matrix is a covariance matrix that has 1s on the diagonal. Right? So that's a concentration matrix. This particular spectrahedron you see every day at NIMS. Right? That's the samosa. So samosa, Indian food. Well, that's this sort of fattened tetrahedron that you see. So you see this picture on the logo for the applied algebraic geometry. There's this yellow convex figure. That's this spectrahedron. Okay. Now, how does this fit into our description? Well, here, the cost matrix is the matrix 0, 2, 3, 2, 0, 5, 3, 5, 0. Yeah, so if you go over this formulation, right, so it turns out, so if you take the inner product, the trace of Cx, and you get that. And there's a factor 2, right? 2, 3, 5 becomes 4, 6, 10, because these entries are twice in the matrix. That's clear? You take that matrix C, you multiply against an unknown matrix X, you take the trace, then that's that. Okay? What's A? So the AI, so A1, for example, is the matrix 1, 0, 0, 0, 0, and likewise A2, A3. So A3 is the matrix that has only the lower triangular entry 1, and otherwise is a 0 matrix. So, is that clear? And then the B's, you know, just for completeness, so the BI's are 1, right? Because the right-hand sides are 1. So X11 is the trace of A1 times X. Okay. Good. Now what about the dual? Let's keep the dual. The dual, this is the primal formulation, and the dual to this is maximize y1 plus y2 plus y3, right? Because the b's are all 1, you know, this is just y1 plus y2 plus y3, subject to, well, what's this one? That's a linear combination, you know, y1, a1 plus y2, a2 plus y3, a3, so that's y1, y2, y3, 0, 0, 0, 0, 0, blah, blah. And that's less or equal in the positive definite sense than 2, 3, 2, 0, 5, 3, 5, 0. Okay? Let me translate this a little bit, rewrite this a little bit more friendly, right? So let me replace each yi by negative zi. So I'm going to introduce new variables, z1, z2, z3. That's the negative. Okay? So then this is equivalent to the following: minimize the trace over all PSD matrices z1, 2, 3, 2, 3, z2, 5, z3, 5. Okay? So it's another way, it's equivalent, right? So take the difference, put the minus sign on every y, right? Then you get this matrix. That's a 3 by 3 matrix where the off-diagonal entries are fixed. They're 2, 3, and 5. The diagonal entries are unknown. And we look at all matrices like this that are positive semidefinite and want to minimize the trace, right? Well, certainly, you know, 0 is a lower bound, right? Because these have to be non-negative. Right? So we look at, you know, how can you make these entries small, right? You want to make the trace as small as possible, but stay positive definite. Okay, so in Berkeley we have this qualifying exam that you have here too, I think, something. But now Berkeley, it's an oral exam, and the students choose their subject. And I was on one in the spring, in February, that was quite memorable. So the student had chosen, you know, optimization and semidefinite, student of Lauren Williams, Stephen Karp. So he had chosen optimization as one of his topics. And so I quizzed them, you know, about semidefinite programming and so on. So then at some point I made him write down an instance, something like this, you know. And I said, well, suppose you want to solve this now. Suppose, you know, in the math building at Berkeley, you know, we have computers and people you can ask. And I give you 15 minutes. You can go out. You can do whatever you want, you know. And, you know, what would you do to solve this problem? Minimize, you know, blah, blah, blah. Okay? So I expected him to say, you know, I would go to MATLAB and try Sedumi, or I run CVX, or something like this. I would say the standard. So the answer I expect would have given him 100 full credit, right? So there exists software. I would type it in MATLAB, and I get the answer. Then that would have been. His answer was by hand. He said I would do it by hand. I said, really? Show me, And he solved it by hand. It was very, very impressive performance. He didn't think of, software, anything. So he proceeded to solve this by hand. So we're going to practice this afternoon. Okay, so this afternoon we're going to practice doing this by hand. Okay, or with a little bit of assistance, I might call it too. This lecture will be structured into 3 pieces. This is the end of the first piece. Let's take a 2-minute break. Now lecture again. Another 2-minute break, and then lecture again. Let's take a 2-minute break.